We begin a new chapter today, and this whole chapter deals with solving systems of linear equations. And there's really three different methods that we're going to discuss throughout this chapter for solving these systems. I think you've been exposed to these methods in Algebra 1, but this is going to be a good, hopefully a good review for you. Today, the focus on solving systems will be on the graphing method. And I'm going to go through some examples like the homework problems in just a moment. But I thought just to start, this is not a slide that you have to write down, but I think it's good to take a step back and see where we've been this year. So far, we've done quite a bit of solving equations. This is a real simple example. Solving this particular equation, we come up with the solution. Remember, a solution is a number that we would plug in for x to make this statement true. So we know how to go about the steps to come up with that solution. There's only one. Notice there's one variable. So I'm going to come up with one solution, and 4 is that solution. So that's kind of a simple illustration of where we've been. And now this is where we're going in Chapter 3. When we solve a system of equations, now we're solving for two variables, x and y. And we're going to use, as I mentioned earlier, one of three different methods to accomplish this. So two equations, notice two variables, we're going to solve for each one. And this is a key point that I need to make is when we do find those solutions for x and y, we have to be sure that the number we substitute in for x and then the other number that we substitute in for y, those numbers not only make the one of the equations true, but they also make the other. In other words, they must make both equations true. Just to give you an example, what if I let x be 2 and y be 1? Well, looking at the first or the top equation, 2 times 2 plus 1, that's 4 plus 1, that's 5, okay? But to be a true solution, x is 2, y is 1 must also make the second equation true. And if we take a look, we get negative 2, that's my x, plus 1. Well, that's negative 1, does not equal 2. So what we've shown here is that even though 2, 1 did make one of these true, it did not make both of these true. Therefore, this is not a solution to the system. Okay, so we're looking for the two variables, x and y, that make both of the equations true in the system. Okay, so again, our method today is going to be strictly the graphing method, and then tomorrow we're going to look at two other, hopefully familiar methods, substitution and elimination. All right, so let's get started. The first thing we should do, since we're going to be graphing really two different lines, is let's get these both equations in slope-intercept form. So I'm going to use colors, and I'll do my lines in the same color as the equation, and then we'll look at see if there is a solution. So this blue equation, I need to solve it for y, and so that means I'm going to have to subtract 2x from both sides. So hopefully we've done enough of these to where you don't really have to see a lot of individual steps. So that is my blue equation, solve for y, or in other words, that is the slope-intercept form. 5 is the y-intercept. So there's 5 on the y-axis. And then from there, I'm going to do a slope of negative 2. So I could go up 2 and left 1. Or I could choose to go down 2 and right 1. I just need a combination of a positive direction and a negative direction, or a negative direction and a positive direction, because a negative divided by a positive is negative. Okay, so let's do this in blue to match the equation. So there's my line. y equals negative 2x plus 5. And now let's set up the red equation. Do the same thing. Let's get it in slope-intercept form. Makes it a little bit easier to graph. So adding x to both sides of this equation to get y by itself, I've got a 2 y-intercept, so here's 2 on the y-axis, and the slope, the number in front of x, is positive 1. So to do a positive 1 slope, I could go up 1 and right 1, 2 positive directions. I could also go down 1, left 1, because a negative divided by a negative is still positive. All right, so let's go ahead. And some people don't like to draw long lines. They're kind of real short. But to give our lines a chance to cross, you might need to lengthen those lines just a little bit, because the whole idea behind the graphing method, if there is a solution, it will be where these two lines cross each other. Okay, and I need for you to show this on your homework graph paper. Don't just give me the two lines in this case, but just take it one small step further and tell me that these two lines cross at 1, 3. So my solution should be x equals 1 and y equals 3. But to be safe, and you can always be sure that you did the right thing, remember, if I let x be 1 and y be 3 in both the blue and the red, that it should make both of these true. So let's just take a quick check. Y is 3, x is 1 in the blue equation. So negative 2 plus 5 is 3. Okay, let's just do a quick check in the red. Y is 3, x is 1. Yeah, and that also checks. So I have confidence now that I've graphed these correctly. My solution for x and y, x is 1 and y is 3. All right, let's try this one. So the red equation, let's solve it for y. That means I'm going to have to subtract x from both sides. And then you can either think of this, to get y by itself, you're either going to divide by 3 on both sides, or you're going to multiply by 1/3. Remember the inverse property of multiplication. So multiplying by 1/3 gives us this. Don't forget that everything is either divided by 3 or multiplied by 1/3. Everything, every term on both sides of this equation. So now this is ready to graph. I need to approximate where 2/3 is on the y-axis, and it's just a little bit below 1. So we'll say it's right there. And then from there, I'm going to count a negative 1/3 slope. So there's two different ways of doing that. I can go up 1, a positive direction, which means I've got to combine that with a negative direction, left 3. Or you could do the negative direction and then combine that with a positive. Right? And I'm going to do this in red. So here is my line for y equals negative 1/3 x plus 2/3. And now let's work on the blue equation. Let's get it solved for y, or slope-intercept form. So the first thing I'm going to do is subtract 3x from both sides. And then I'm going to divide by 3 on both sides, meaning every term. Negative 3 divided by 3 is negative 1x. Negative 6 divided by 3 is negative 2. Okay, so I start off with a y-intercept of negative 2, which is right there. And then I have a slope of negative 1. Okay, and you really just need 3 points on your line, but I did a little extra. Okay, get a running start, and here is the blue equation. Okay, well, the solution to a system using the graphing method should be the intersection, if there is a solution, it'll be where these two lines cross, which looks like it's right there. So the ordered pair of that point of intersection is -4 and then +2. Okay, and that ends up being the solution. And we could take the time to check it if we wanted to. I encourage you to, if you want to be sure, 100% sure that this is correct. Then when you let x become -4 and y become +2 in both the red and the blue, these two numbers for x and y should make both of these equations true. Let's try this one. Let's start with the blue, and we'll get this solved for y, slope-intercept form. -4x plus 12, and then I'm going to either divide by 8 or multiply by 1/8. Either way you look at it, -4 divided by 8 is -1/2 x. And then we got 12 divided by 8, which is 3/2 reduced. Just in case you don't see that, 12 over 8. Both of these numbers can be divided by 4. 12 divided by 4 is 3. 8 divided by 4 is 2. Okay, so 3 over 2 is another way of saying 1 and 1/2. So for graphing purposes, we might want to think of that as a mixed number. There's 1 and 1/2, close to it. And then from there, I'm going to count a slope of -1/2. So I'm going to go up 1 and left 2. You could have also done down 1 and right 2. And let's sketch this line. Okay. And now let's work on the red equation, getting it solved for y. So the first thing I'm going to do is subtract x from both sides. Then I'm going to divide by 2 on both sides, or multiply by 1/2. And something interesting happens. I notice that when I compare the red equation and the blue equation, they have the same slopes. And we know from our past experience that when lines have the same slopes, they are parallel to each other. They will never cross. So we do need to go ahead and sketch the graph. So let's plot a -1.5 y-intercept and a -1/2 slope, up 1, left 2. Okay. And let's draw the red line that corresponds to the red equation. Okay, well, we said earlier that the solution to a system of linear equations using the graphing method would be where two lines cross. Well, if they don't cross, and parallel lines will never cross, that means we do not have a solution. So I need for you to say that on your graph paper. Graph the two lines showing that they're parallel, and then since they do not cross ever, and you knew that by looking at the equations because parallel lines always have the same slope and they have different y-intercepts. Okay, so we've looked at an occasion where the two lines cross at a definite point. Our previous example showed two lines that never cross, and that means we don't have a solution. Well, let's look at the third possibility. The third possibility would be, well, let's just go ahead and graph these two. The blue one is already in slope-intercept form, so that's nice. We don't have to work to solve it for y. It's got a y-intercept of 3 and a slope of -1/4, so I'm going to choose to go up 1, meaning I've got to go left 4. Or maybe you thought go down 1, so you're going to have to go right 4. Okay. Up and left 4. And there's the blue equation. All right, the red equation needs a little work to get it solved for y, so let's subtract x from both sides. And lo and behold, when I divide or multiply by 1/4 on both sides, I end up with the exact same equation as the blue. And so this is a system that really didn't look like it maybe at the outset, but it turns out that it's just the same equation both times. So if I were to graph the red, it would just be that same line. Okay, so here's what happens. Here's the interpretation of this. Any ordered pair on this line will make this system true. Okay, it really doesn't matter what ordered pair I decide to pick, as long as it's on this line. Then when I let X go in and Y be replaced from ordered pairs off of this line, then it will make this equation true. Okay, since lines never stop, you can tell by my arrows, this line continues forever and ever in both directions. So there is no possible way to come up with all of the ordered pairs on a line. We would spend the rest of our life and we would still not have them all, because this line goes to positive and negative infinity. So the way we're going to represent our answer, interpret our answer, is we're going to say that there is an infinite number of solutions. All of the ordered pairs that could be pulled from this line, and there's an infinite number. So I'm okay if you want to abbreviate infinite number of solutions. You can just say INS for this situation. So we've looked at three possibilities. Crossing at a definite point, there's the solution. Never cross, no solution. Really just the same line. If you think about it, it's like one line and then you graph the same line on top of it. So any ordered pair off of this line would be a solution, and there's more than we could ever count. So there's an infinite number. All right, so check RenWeb for your homework. Notice that some of these graphs, the last three, are taken from a section in your book, and we're changing the directions. I just want you to practice graphing. So ignore the directions in your book. I gave you a note to this effect on RenWeb, so make sure you check that out. And if you have any questions about this, just let me know.